All right, back by popular demand. So thanks so much to the commenters for encouraging me to keep on with this book, AI for network engineering. It's hard to read books like these, and then, I'm a network engineer, so like I always have this push to pull of like, what should I even be doing? But I'm enjoying the book. The database of tools is just absolutely pure gold from the book. So I have that linked, I think, in either part seven or part six. It looks like it's not part. Looks like neither of those. It's going to be in uh, part well, not in part five either. So I guess it's really buried by now. But anyways, there's that tool of GitHub repositories that have open source code used to deploy local models. So really, really, well, and it's not necessarily only local as well. In fact, a lot of them aren't, but a lot of them you'll have to pay for the OpenAI API or API from another one. But you should be able to run it locally as well. But then that doesn't save you money too because you have to have the hardware to run it like locally. So you'll have to spend on at least a state-of-the-art gaming PC, if not, something with far more hardware capacity beyond that. So, if you really want to do an AI project, the best way probably is to just bite the bullet and pay for those uh, those APIs. Um, and it might be worth it many times over. I mean, a certification exam from my world, the CCNA, that can be $400 just for the exam alone, and then that's not even accounting for the training. I mean, the book itself that can be anywhere from 60 to $100, even more. The lab tools, I mean, you can easily be on the hook for over $1,000 just to get, a basic associate level certification in the industry, like the CCNA. So if you think of it that way, it's like, how much is even like $100 to spend on a LLM project that you can use to maybe get yourself hired to an AI engineer role to put yourself above the pack of applicants. For $100, that's a steal. Like if you compare it to something like getting your CCNA or like going to a boot camp or a 2-year college or a 4-year college. Like uh, like I'm trying to reframe my own thinking to see these sorts of things more like that. I'm a cheapskate, so I'm having trouble doing that. But yeah, I mean, like a lot of the and then the thing is, a lot of these projects, like you can walk away with a really solid project that puts you at the front of the pack for like a job application, and you can walk away having spent like $30. So that's just my take of it when it comes to these APIs. Like, yeah, it sucks that you've got to put your to do any, pay to play. Anything you do, you have to spend money to make money. That sucks. I hate that because it gives an unfair advantage to people who can indiscriminately spend, and because it uh impedes your access to education, which I believe should be a basic human right. But when you look at the potential value of it, um, if you can get away with spending $30 to make an AI project, I mean, come on, like there's no justification to just say, oh, I'd rather not spend that $30. And I would say that the price tag for that goes up to 400 because when you look at a certification, that can be at 400 just for the exam fee alone, you know 500 once you bought the book, and then way well beyond 1,000 once you've bought the extra supplemental study materials like CBT nuggets, like I&E that oftentimes you need in order to pass. You can't pass without buying some supplemental materials. So, $100 to 400 is probably a range that you should consider for spending on a LLM project that you're going to use to demonstrate your value to an employer to get hired. Anything under $100, just do it. I'd say don't even think about it. And then over that 500, you should even probably consider that as well. So not financial advice, but it's just kind of I'm talking about my own thinking of this because I definitely have a hang up where the moment I see that I have to pay 50 cents for an API or you know like 50 cents to do an AWS project, just the moment I'm like, well, my learning is done, and it's silly, and I have to overcome that if I want to be successful in my career. I need to be able to appropriately value um, place the appropriate value on learning. All right, so moving on, hyperparameter versus, oh sorry, parameter versus hyperparameter. And let's just start here with scaling extrapolation. The performance of a model depends heavily on the parameters on the values of its hyperparameters. When working with small models, it's a common practice to train a model multiple times with different sets of hyperparameters and pick the best performing one. This is, however, rarely possible for large models as training them once is resource draining enough. Parameter versus hyperparameter. A parameter can be learned by the model during the training process. A hyperparameter is set by users to configure the model and control how the model learns. Hyperparameters to configure the model include the number of layers, the model dimension, and vocabulary size. Hyperparameters to control how a model learns include batch size, number of epochs, learning rate, per layer initial variance, and more. This means that for many models, you might have only one shot of getting the right set of hyperparameters. As a result, scaling extrapolation, also called hyperparameter transferring, has emerged as a research subfield that tries to predict for large models what hyperparameters will give the best performance. The current approach is to study the impact of hyperparameters on models of different sizes, usually much smaller than the target model size, and then extrapolate how these hyperparameters would work on the target model size. A 2022 paper by Microsoft and OpenAI shows that it was possible to transfer hyperparameters from a 40 million model to a 6.7 billion model. Scaling extrapolation is a niche topic, as few people have the experience and resources to study the training of large models. It's also difficult to do due to the sheer number of hyperparameters and how they interact with each other. If you have 10 hyperparameters, you'd have to study 1024 hyperparameter combinations. You would have to study each hyperparameter individually, then two of them together, and three of them together, and so on. In addition, emergent abilities, Wei et al. 2022, make the extrapolation less accurate. Emergent abilities refer to those that are only present at scale. So, emergent abilities refer to those that are only present at scale, might not be observable on smaller models trained on similar data sets. I feel like that could be written more clearly. I kind of don't under. I get what they're saying. So emergent abilities refer to abilities that are only present at a certain scale and might not be observable on smaller models trained on smaller data sets because they do not reach that level of scale. They're too small. Like I feel like that could be rewritten to be a lot clearer, but at the same time, like I feel like it's clear enough, even though it's very awkward to read. To learn more about scaling extrapolation, check out this excellent blog post on the difficulty of extrapolation with neural network scaling by Luke Metz. And I think Luke Metz, is that a familiar name? Uh, no. No, that's not. In Situational Awareness by Leopold Aschenbrenner, there was a researcher that he was fawning over. Um, and it looks like there's over 100 matches for researcher, so maybe I won't find um, maybe I won't find the name of this researcher. Well, basically, what he did in this is he singled out, what he thought, who he thought was the highest quality AI researcher alive, and it wasn't. Here we go. Found it. Alec Radford is an incredibly gifted and prolific researcher slash engineer at OpenAI, behind many of the most important advances. Although he flies under the radar some, he doesn't care about having a public presence, so therefore he basically doesn't have one. So, um, okay, that's who I thought this might have been, this Luke Metz, but no, it's someone else. But yeah, this is who Leopold Aschenbrenner thought was probably one of the most talented people at OpenAI. Uh, I am following him already. Oh, and he doesn't work at OpenAI anymore. Nobody works at OpenAI anymore. Oh, is this the right person? Oh, that's interesting. Huh. I don't know if this is the right person. Oh, yeah, it is. Okay, same picture. Yeah. Yeah, I guess he just doesn't have his OpenAI experience on his LinkedIn. Well, as he said, I'm sure he hasn't updated it in forever. In fact, we can probably see. Yeah, he first wrote it down in 2013, and he probably hasn't updated it. So he probably got hired to OpenAI afterwards, and like this is probably one of his first like work experiences, head of research. So he started, yeah. Okay, but yeah, you can see all of his papers on Google Scholar. Um, yep. Looks like he does have a Twitter that oh nope, he's hasn't posted on Twitter for 5 years. I think he does have a blog that's like pretty good. Let me see. Yeah, artificial-intelligence.blog. I think he does up, yeah, so yeah. 2024 12/20. There we go. Alec Radford, an OpenAI researcher, helped develop some of the most important artificial intelligence. Told colleagues he was leaving to pursue research independently. Um, Okay. So it looks like this is a blog that is kept it's not autobiographical, it's more biographical. So it's written about him by someone. It's almost like a fan club, which is kind of odd. But it's cool because you can see they've got a lot of education videos here. Um, like it seems like a pretty decent resource. Yeah, so they've got Dwarkesh's podcast, which is excellent. Wes Roth, which is really awesome. So all the good stuff that should be on people's radar who is interested in AI is on here. All right, so there that's to go into more depth. It's by Luke Metz, who I haven't really heard of, but it's too much. I just want to get the book done. So moving on. Scaling bottlenecks. Until now, every order of magnitude increase in model size has led to an increase in model performance. GPT-2 has an order of magnitude more parameters than GPT-1, 1.5 billion versus 117 million. GPT-3 has two orders of magnitude more than GPT-2, 175 billion versus 1.5 billion. Um, this means a three orders of magnitude increase in model sizes between 2018 and 2021. Three more orders of magnitude growth would result in a 100 trillion parameter models. And Leopold Aschenbrenner in situational awareness says we're going to get that very soon by about 2027. How many more orders of magnitude can model sizes grow? Would there be a point where the model performance plateaus, regardless of its size? While it's hard to answer these questions, there are already two visible bottlenecks for scaling: training data and electricity. Yeah, but there are approaches that might make it so that the bottlenecks don't bottleneck. Like for example, for training data, while you don't need it's the amount of data that's bottlenecked, but the quality of data, we still have all kinds of advancements we can make in feeding it quality data to be trained on. I mean, that's still very much unexplored. And then electricity, like, they're restarting up 3 Mile Island. They're like adding nuclear power to data centers. So electricity, I would say, in my opinion, is going to be a bigger one than training data. Electricity, I would say, is a real bottleneck because in situational awareness by Leopold Aschenbrenner, he had a whole section saying that when it comes to our climate change pledges and commitments, um, if we want to be a world leader in AGI, like we're just gonna have to be like bad about it. We're gonna have to be like really bad about our commitments. There's a whole section that says like, you know, like basically if we want to be the first to AI, which we should probably do because for all of its flaws, and when I say we, I mean the United States, and that's important to note too about situational awareness. It's very U.S. centric, much in the way I am talking now. But for me, as a U.S. citizen, uh, I want my country to be first to AI. But to do that, it's going to have to overcome that electricity bottleneck. And the only way we have to do that in a way to stay competitive with other countries like China that have vastly more growth in their electricity than in the United States is to go back on our climate pledges and use our natural gas resources. Um, so it kind of puts somebody like me that really thinks we should have a or like that really wants us to take climate change seriously and to uphold our agreements and pledges. It kind of puts me in a difficult situation because at the same time I want that, I think I want to be first to AI as well. Not only because I want to use AI and I benefit from using AI, but because I don't want other countries that don't share my same sorts of value systems to get to AGI faster. So it, it's a tough situation, and that was probably one of my most thought most thought-provoking. That was probably for me one of the most thought-provoking parts of situational awareness. Well-intentioned but rigid climate commitments, not just by the government, but green data center commitments as well, stand in the way of obvious, fast solutions to overcoming that electricity bottleneck. For example, we could do natural gas. Um, uh, we could do solar. We could even do like solar in a more robust way. Um, yeah, yeah, we could get rid of all the regulations. It's just, so that's basically long story short, and without getting into more contentious, without putting all of my opinions out there. This is why I would say for me, uh, electricity seems like a pretty big bottleneck to AI in the United States at least. So foundation models use so much data that there's a realistic concern we'll run out of the internet data in the next few years, which I don't think matters at all. We need quality of data, not quantity. The rate of training data set size growth is much faster than the rate of new data being generated. Villalobos et al., 2022, as illustrated in Figure 2-9. If you've ever put anything on the internet, you should assume that it already is or will be included in the training data for some language models, whether you consent or not. This is similar to how if you post something on the internet, you should expect it to be indexed by Google. Yeah, and you should also expect not to be compensated for that either, which is the sad, sorry truth. I mean, I've been using ChatGPT every day, all the time. I'm reading these books, and not only, will I not be compensated for the time that I'm um, doing using the ChatGPT product, which is, a little bit in beta still, um, and the time I'm spending reading these books, I actually might even be at risk for like some sort of copyright and not WRIGHT copy like for violating some sort of intellectual property sort of thing. So it's kind of a yeah. So it's kind of an odd world we're in now, where like it's always been hard to make it as an artist, but AI might make it become even harder. So here's a graph here. So the y-axis is effective stock, number of tokens, and then the x-axis is year. So we can see as time goes on, these are the predictions. So the year now is 2025. So we can see this is exactly what situational aware. This is situational awareness in one graph. By the year 2027, before the end of the year 2027, uh, we're going to have a model that is 2 orders of magnitude in size as the one that we have today. So that would be like going from ChatGPT 2, or like going from GPT 2 to we're gonna go from here to here for like soon. Like it is not done yet, and it's multifaceted. Not any one bottleneck isn't gonna shut it down. So yeah, this is situational awareness in one graph here. But we can see this shows the stock of data. So this is how much data they're predicted there is, and we can see this is showing the bottleneck. So we've got the median date of the full. So it might be bottlenecked for a bit of time after that. It might not, but I mean, come on, like 2027, 2028, like this is significant, right? Like this will change the world. But yeah, it might start slowing down a bit after that, but at the same time, again, like quality of data is much more important than quantity. In fact, in most educational programs in schools, they give you curriculums that reduce like what you could read rather like they when you go to math class, oftentimes you only learn about geometry or algebra and not all of math all at once. So to have a restriction in the stock of data might actually help improve AI rather than bottleneck it. So figure 2-9 projection of historical trend of training dataset sizes and available stock data. Some people are leveraging this fact to inject data they want into the training data of future models. They do this simply by publishing the text they want on the internet, hoping it will influence future models to generate the responses they desire. Bad actors can also leverage this approach for prompt injection attacks, as discussed in Chapter 5. Note, an open research question is how to make a model forget specific information it has learned during training. Imagine you published a blog post that you eventually deleted. If that blog post was included in the model's training data, the model might still reproduce the post's content. As a result, people could potentially access removed content without your consent. On top of that, the internet is still being rapidly populated with data generated by AI models. If companies continue using internet data to train in future models, these new models will be partially trained on AI generated data. In December 2023, Grok, a model trained by X, was caught refusing a request by saying that it goes against OpenAI's use case policy, despite it not being a product bound by OpenAI's use cases policy. This caused some people to speculate that Grok was trained using ChatGPT outputs. Igor Babushkin, a core developer behind Grok, responded that it was because Grok was trained on web data and the web is full of ChatGPT outputs. Some researchers worry that recursively training new AI models on AI generated data causes the new models to gradually forget the original data patterns, degrading their performance over time. However, the impact of AI generated data on models is more nuanced and is discussed in Chapter 8. Once the publicly available data is exhausted, the most feasible paths for more human-generated training data is proprietary data. Unique proprietary data, copyrighted books, translations, contracts, medical records, genome sequences, and so forth, will be a competitive advantage in the AI race. This is a reason why OpenAI negotiated deals with publishers and media outlets, including Axel Springer and the Associated Press. It's not surprising that in light of ChatGPT, many companies, including Reddit and Stack Overflow, have changed their data terms to prevent other companies from scraping their data for their models. A research paper in 2004 observed that between 2003 and 2004, the rapid crescendo of data restrictions from web sources rendered over 28% of the most critical sources in the popular public dataset C4 fully restricted from use. Due to changes in its terms of service and crawling restrictions, a full 45% of C4 is now restricted. And the sad part is, if I remember correctly, we read about just how bad C4 is, how much garbage there is in C4 that's not useful for training. So if the good stuff is going to be the stuff that is removed from C4, the rot of C4 might be all that remains. And I would think it's more likely that those that wrote really good stuff are those more likely to have terms of service and restrictions that make it not get into the C4. The people just writing garbage don't know how to do that or don't have any reason to. So that's concerning. The other bottleneck, which is less obvious but more pressing, is electricity. Yeah, and that's the big one. Machines require electricity to run. As of this writing, data centers are estimated to consume 1 to 2% of global electricity. This number is estimated to reach between 4% and 20% by 2030. Until we can figure out a way to produce more energy, data centers can grow at most 50 times, which is less than two orders of magnitude. This leads to a concern about a power shortage in the near future, which will drive up the cost of electricity. Now that we've covered two key modeling decisions, architecture and scale, let's move on to the next critical set of design choices, how to align models with human preferences. That's funny. All right, so I do need a break at some point. Probably only at the. Oh, okay, we're at the 30-minute mark. And I need to cut off at 6. So perfect time for a 5-minute break. I'll be right back. All right, welcome back. I've still got some time here. So let's see here. So yeah, so post training. Post training starts with a pre-trained model. Let's say that you've pre-trained a foundation model using self-supervision. Due to how pre-training works today, a pre-trained model typically has two issues. First, self-supervision optimizes the model for text completion, not conversations. If you find this unclear, don't worry. Supervised fine-tuning will have examples. Next, if the model is pre-trained on data indiscriminately, scraped from the internet, its outputs can be racist, sexist, crude, or just wrong. And in fact, I would say that the outputs, um, if there's that sort of crackdown on C4, where you know authors who are distinguished and you know want to protect their writings, put them away, lock them away. Now all there's going to be on the internet is the racist, sexist, rude, or just plain wrong data that people are trying to force people to read rather than uh, withholding people from reading until they pay. like People who support those kinds of outputs are more than happy that you have access to them and read them at any price. The goal of post training is to address both of these issues. Every model's post training is different. However, in general, post training consists of two steps. Number one, supervised fine tuning, SFT. Fine tune the pre trained model on high quality instruction data to optimize models for conversations instead of completion. Number two, preference fine tuning. Further fine tune the model to output responses that align with human preference. Preference fine tuning is typically done with reinforcement learning, RL. Techniques for preference fine tuning include reinforcement learning from human feedback, RLHF, used by Chet, used by GPT 3.5 and Llama 2, DPO, direct preference optimization, used by Llama 3, and reinforcement learning from AI feedback, RLAIF, potentially used by Claude. Let me highlight the difference between pre-training and post-training another way. For language-based foundation models, pre-training optimizes token level quality, where the model is trained to predict the next token accurately. However, users don't care about token level quality. They care about the quality of the entire response, and not the response per token. Post-training in general optimizes the model to generate responses that users prefer. Some people compare pre-training to reading to acquire knowledge, while post-training is like learning how to use that knowledge. Warning, watch out for terminology ambiguity. Some people use the term instruction fine-tuning to refer to supervised fine-tuning, while some other people use this term to refer to both supervised fine-tuning and preference fine-tuning. To avoid ambiguity, I will avoid the term instruction fine-tuning in this book. As post-tuning consumes a small portion of resources compared to pre-training, Instruct GPT used only 2% of compute for post-training and 98% for pre-training. You can think of post-training as unlocking the capabilities that the pre-trained model already has, but are hard for users to access via prompting alone. Figure 2-10 shows the overall workflow of pre-training, SFT, which we remember stands for supervised fine-tuning, and preference fine-tuning, assuming you use reinforcement learning from human feedback for the last step. You can approximate how well a model aligns with human preference by determining what steps the model creators have taken. Okay, so so we've got low quality data from the internet, from W2, wherever, or not W2, C2. So it would be yeah, the mechanism that scrapes the internet, the database maintained by that. That would be very low quality data, and it's optimized for completion. Self-supervised pre-trained model. Then that gets fine-tuned. So high quality data gets added to it, demonstration data. And this is why I don't think there's going to be that much of a bottleneck due to data for electricity for sure. But I think this high quality demonstration data will get quite bigger as time goes on. So you've got fine-tuned for dialogue. That's supervised fine-tuning, and then the SFT model gets fed into reinforcement learning from human feedback. So supervised fine-tuning, fine-tune the pre-trained model on high-quality instruction data to optimize models for conversations instead of completing. So then we get human feedback. So asses and seats, comparison data, trained to give a scalar score for prompt, comma, response. We get classification reward model. Then we get prompts optimized to generate responses that maximizes scores by reward model. Reinforcement learning. which can be fed directly to that, and then the final model. So figure 2-10, the overall training workflow with pre-training, SFT, and RLHF. If you squint, figure 2-10 looks very similar to the meme depicting the monster Shoggoth with a smiley face in figure 211. So let's look at that. Skip ahead and look at that. Oh, funny. So unsupervised learning is this big scary monster. Supervised learning is another scary monster that's an offshoot from the really big scary one. And then RLHF is just kind of a part that looks like it's not so scary, but it really is when you look beyond it. Number one, self-supervised pre-training results in a rogue model that can be considered an untamed monster because it uses indiscriminate data from the internet. Number two, this monster is then supervised, fine-tuned on higher quality data, Stack Overflow, Quora, or human annotations, which makes it more socially acceptable. Number three, this fine-tuned model is further polished using preference fine-tuning to make it customer appropriate, which is like giving it a smiley face. So figure 2-11 showed the Shoggoth with a smiley face meme, adapted from an original image shared by that person. And what platform was this originally shared on? X. All right, so note that a combination of pre-training, SFT, and preference fine-tuning is the popular solution for building foundation models today, but it's not the only solution. You can skip any of these steps, as you'll see shortly. Supervised fine-tuning. As discussed in Chapter 1, the pre-trained model is likely optimized for completion rather than conversing. If you input how to make pizza into the model will continue to complete this sentence, as the model has no concept that this is supposed to be a conversation. Any of the following three options can be a okay, a valid completion. Adding more context to the question. For a family of six, asking follow-up questions. What ingredients do I need? How much time would it take? Giving the instructions on how to make pizza. If the goal is to respond to users appropriately, the correct option is three, but you can imagine how the model would have no way of knowing the correct option would be three, especially if you left off the punctuation. Then in that case, the correct answer would the next token prediction, would be not a capital letter because it's not the start of a new sentence. So you'd only get an answer like valid completion number one. We know that a model mimics its training data. To encourage a model to generate the appropriate responses, you can show examples of appropriate responses. Such examples follow the format prompt, comma, response and are called demonstration data. Some people refer to this process as behavior cloning. You demonstrate how the model should behave, and the model clones this behavior. Since different types of requests require different types of responses, your demonstration data should contain the range of requests you want your model to handle, such as question answering, summarization, and translation. Figure 2-12 shows a distribution of tasks of types of tasks OpenAI used to fine-tune their model InstructGPT. Note that this distribution doesn't contain multimodal tasks, as InstructGPT is a text-only model. Okay, so primarily they used generation tasks to fine-tune the model, but that's the model InstructGPT, which is a different model. Yeah, so mostly generation. So figure 1-12, the distribution of prompts used to fine-tune instruct GPT. The graph is created based on the numbers from the OpenAI paper. Good teachers are important for humans to learn. Similarly, good labelers are important for AIs to learn how to conduct intelligent conversations. Unlike traditional data labeling, which can often be done with little to no domain expertise, demonstration data may contain complex prompts whose responses require critical thinking, information gathering, and judgment about the appropriateness of the user's requests. Table 2-6 shows examples of prompt comma response pairs created by labelers for Instruct GPT. So table 2-6 is below and it shows examples of demonstration data used for Instruct GPT. And this demonstration data can come from many places. It can come from classification, rewrite, chat, brainstorming, open QA, closed QA, but primarily it comes from generation. So the prompt would be serendipity, means the occurrence and development of events by chance in a happy or beneficial way. Use the word in a sentence. So the label's response would be running into Margaret and being introduced to Tom was a fortunate stroke of serendipity. Next prompt, read the following text and answer the three questions at the end. So, omitted for length, this is an article about Justice Ruth Bader Ginsburg, champion of gender equality, dies at 87. So, shortening it up. So, the third one is why will Ginsburg's death have profound consequences for the court and the country? Number three. So um, Ruth Bader Ginsburg was the leader of the liberal ring, and because the court is about to open a new term, the Chief Justice no longer holds the controlling vote in contested cases. Yeah, yeah. So if it put that as number two, or if it got key facts incorrect about Ruth Bader Ginsburg, that would be bad demonstration data, and it would be a bad response. But yeah, so okay. So ELI5. What's the cause of the anxiety lump in our chest during stressful or disheartening experiences? The anxiety lump in your throat is caused by a muscular tension keeping your glottis diluted to maximize airflow. This clenched chest or heartache feeling is caused by the vagus nerve, which tells the organs to pump blood faster, stop digesting, and produce adrenaline and cortisol. So companies therefore use highly educated labelers to generate demonstration data. Among those who labeled demonstration data for Instruct GPT, around 90% have at least a college degree, and more than one-third have a master's degree. If labeling objects in an image might take only seconds, generating one prompt comma response pair can take up to 30 minutes, especially for tasks that involve long contexts like summarization. If it costs $10 for one prompt comma response pair, the 13,000 pairs that OpenAI used for Instruct GPT would cost $130,000. That doesn't yet include the cost of designing the data, what tasks and prompts to include, recruiting labelers, and data quality control. Not everyone can afford to follow the high quality human annotation approach. LAION, a nonprofit organization, mobilized 13,500 volunteers worldwide to generate 10,000 conversations, which consist of 161,443 messages in 35 different languages, annotated with 4,461,292 quality ratings. Since the data was generated by volunteers, there wasn't much control for biases. In theory, the labelers that teach models the human preference should be representative of the human population. The demographic of labelers for Leon is skewed. For example, in a self-reported survey, 90% of volunteer labelers identified as male. Yeah, and that's important. Yeah, to get those labelers. Yeah, because a lot of it is judgment stuff too, where you know it's there is no clear answer. All right, so DeepMind used simple heuristics to filter for conversations from internet data to train their model Gopher. They claimed that their heuristics reliably yield high quality dialogues. Specifically, they looked for texts that look like the following format. So there we go. To reduce their dependence on high quality human annotated data, many teams are turning to AI generated data. Synthetic data is discussed in Chapter 8. Technically, you can train a model from scratch on the demonstration data instead of fine tuning a pre trained model, effectively eliminating the self supervised pre training step. However, the pre training approach often has returned superior results. All right, and I do need to wrap it up at 6. Uh, so I think I can get through this next section. Preference fine tuning. With great power comes great responsibilities. A model that can assist users in achieving great things can also assist users in achieving terrible things. Demonstration data teaches the model to have a conversation, but it doesn't teach the model what kind of conversation it should have. For example, if a user asks the model to write an essay about why one race is inferior or how to hijack a plane, should the model comply? In both of the preceding examples, and it gets even trickier than that, right? Because what if the user asks the model to help them play GTA 5, and part of that is hijacking a plane in the game? Should they comply with that? What if some of the instructions for how to do that in the game overlap with how you could actually do it in real life? Should the model apply to that? What if the person already knows, or it's already kind of widely known how to do that, but this specific person doesn't know? Should the model tell that person? What if that person is the one person out of a million people who's crazy enough to actually go and do it, and the only thing holding them back is they were so crazy that they were kind of cut off from the world, and this is their only this is the first time they've ever heard of the you know the idea that the cockpits aren't locked, and it was the only thing holding them back from hijacking a plane. It gets complicated. In both of the preceding examples, it's straightforward to most people what a model should do. However, many scenarios aren't as clear cut. People from different cultural, political, socioeconomic, gender, and religious backgrounds disagree with each other all the time. How should AI respond to questions about abortion, gun control, the Israeli Palestine conflict, disciplining children, marijuana legality, basic universal basic income, or migration? How do we define and detect potentially controversial issues? If your model responds to a controversial issue, whatever the response is, you'll end up upsetting some of your users. If a model is censored too much, your model may become boring, driving away uh, users to. And the other thing is, with censoring your model too much, your users are going to gravitate to the models that aren't censored, and those models might be uncensored for a reason, because they're trying to drive a ideology or because they're malicious models. So if you censor too much, you might be driving, you might be making the very problem you're trying to avoid worse, because you're driving uh, users to seek out models made by people that aren't so ethical as you are to have censored your model. Fear of AI models generating inappropriate responses can stop companies from releasing their applications to users. The goal of preference fine-tuning is to get AI models to behave according to human preference. This is ambitious, if not impossible. This is an ambitious, if not impossible goal. Not only does this assume that universal human preference exists, but it also assumes that it's possible to embed it into AI. Had the goal been simple, the solution could have been elegant. However, given the ambitious nature of the goal, the solution we have today is complicated. The earliest successful preference fine-tuning algorithm, which is still popular today, is RLHF, which stands for Reinforcement Learning from Human Feedback. RLHF consists of two parts. Number one, train a reward model that scores the foundation model's outputs. Number two, optimize the foundation model to generate responses for which the reward model will give maximal scores. While RLHF is still used today, newer approaches like DPO are gaining traction. For example, Meta switched from RLHF for Llama 2 to DPO for Llama 3 to reduce complexity. I won't be able to cover all the different approaches in this book. I choose to feature RLHF instead of DPO here because RLHF, while more complex than DPO, provides some flexibility to tweak the model. Llama 2's authors posited that the superior writing abilities of LLMs, as manifested in surpassing human annotators in certain tasks, are fundamentally driven by RLHF. So yeah, you can think of it. I mean, they're trained by some of the smartest people out there, right? We saw what their trainers were like. They were people with, at minimum, bachelor's degrees, if not master's degrees. So, you know, of course they're going to have really good abilities to write because they've been educated quite well. All right, so with that, I want to give myself plenty of time. I need to be somewhere tonight, and I don't want to be scrambling at the last minute to get out the door. Uh, so by popular demand, here's another video. And I'm almost right at that hour mark, which is typically all I'm good for. So yeah, I'll try to keep these coming more often. And I apologize, I've been away for a few days. But yeah, I'm liking this book and no plans to quit. So stay tuned for the next video.